Now, the whole reason for defining this extent of reaction is that we want to keep track of what's happening with our reaction as it's occurring. We want to be thinking about how do we find the change in the moles of A. What's that change going to look like? And that change is not going to depend so much on the initial amounts of moles that we have. It's going to depend more on this extent of reaction. Just one side note on extent of reaction. The units for this, I want you to pause and think, what are the units of Xi? Hopefully you took a chance to think about that. The units of this has to be in moles to be able to match the units of the rest of this equation. Right, so because NB and NB naught, those are in moles, and the stoichiometric coefficients have no units, so therefore extent of reaction has to be in units of moles for everything to work out. Okay, so what we want to keep track of in terms of thermodynamics, if we're doing a reaction at constant temperature and pressure, which is most often what we are doing in chemistry, then we want to be thinking about what is the change in the Gibbs energy, right? How does G change as the reaction changes? The reaction is going to proceed in a way that will minimize the Gibbs energy because that's what's going to be the spontaneous process until the change in Gibbs energy goes to zero, right? Delta G goes to zero. That's our condition for equilibrium. So we can go ahead and write out what variables does G depend on. Well, G is going to depend on the temperature and the pressure, and it will also depend on how many moles we have of our different substances. So in our reaction here, we need to consider the moles of our two reactants, A and B, and our two products, Y and Z. So if we want to write out the complete differential of the Gibbs energy, we're going to have terms that depend on how does G change with temperature, keeping pressure and everything else constant. I'm not going to write out all the n's, right, dt. Then we'll also have a dg dp at constant t and all the n's dp. All right, so we've seen these before already. And then we'll have a bunch of terms that depend on our number of moles. So we'll have dg dna, keeping t and p and all the other n's constant. And similar terms for our other reactant B, keeping everything else constant, dnB, dg dny, keeping t, p, etc. constant, and finally one for Z. Okay, and now this is our total differential. We got a long equation here. So we've seen equations like this before, and so we can recognize that we have some things we've seen before, right? So all of these dg, dna, dn terms, these are all just chemical potentials for our particular reactant or product that we're considering. We know that this partial derivative is equal to minus s. This one is equal to v. This just comes from our definition of dg that we've seen before. Let me keep that there. And we can write this out as dg equals minus s dt plus v dp plus mu a dna plus mu b dnb plus mu y dny plus mu z dnz. Right, so that is what's going to affect how our Gibbs energy changes as a function of all these variables. Now, if we consider constant T and P, which is usually what we're considering for chemical reactions, these first two terms will go to zero because dt will be zero and dp will be zero. And so what is going to matter for our equilibrium, for our reaction, is our Gibbs energy is going to change depending on how the chemical potentials and the number of moles change. Right, so we'll have just all of our mu a dna terms plus mu b dnb plus mu y dny plus mu z dnz. Let me write that as actual d. Okay, so what we have is that our changing Gibbs energy depends on the chemical potentials and how the moles are changing. And to be able to sort of complete this expression, we'd like to write out an expression for what are how do our moles change, right? What is the value of this differential DNA? So if we go back to our definition above, we have Na was equal to Na naught, which is some constant, plus nu A, right, our stoichiometric coefficient, times the extent of reaction. So if we, oh wait, and that's not plus, that's a minus. Right, so if we take a differential here of this expression, we'll have dNA. Well, the differential of our initial moles is 0 because this is a constant. And so we will just end up with our constant stoichiometric coefficient times the change in the extent of reaction, d psi. And we can write similar expressions for all of the other components of our reaction mixture here. So we'll have DNA looks like this, where it's negative. DNB will look essentially the same with the proper stoichiometric coefficient. Whereas for our products, Y and Z, these will be positive with the way we've defined things. Let's see if I can fit this. There we go. Okay, and so we can substitute this into our initial expression, or our expression up here. Make substitutions for all these dn values, and we get dg is equal to minus nu a mu a d psi minus nu b mu b d psi. And you can see the power of the extent of reaction here is now everything's all in terms of the same variable. We don't have a bunch of different n's that we're worrying about. Everything's in terms of this extent of reaction. So that's why, this is why we defined it the way we did. All right, and then we have positive terms for our products. Okay. And so in the next video, we'll look at how we can go from this to something that you're more familiar with, and how we can relate this expression, how it leads us to the equilibrium constant that you are familiar with.